Hi, Dr. Robin here. Today we're going to be talking about energy in nuclear reactions. When you think about nuclear energy, you probably think of a big power plant like this, something producing energy on a large scale. But the foundation of nuclear energy occurs on a much smaller scale, down in the nucleus of an atom. So let's talk about that now, a story that I call
The Mystery of the Missing Mass.
Let's look at a very small atom, lithium-7. Now, if you think back to your isotope symbols, you might recall that this 3 here means that this isotope has 3 protons. Each of those protons has mass. They weigh about 1.0073 unified atomic mass units each, for a total of 3.0219 U. This 7 here is the mass number, which tells us that we have 7 total nucleons, which means protons and neutrons. If we subtract 3 to account for the protons we already know about, we calculate that we have 4 neutrons. Again, each of these have mass, about 1.0087 unified atomic mass units apiece. So that gives us 4.0348 U of neutron mass. We can add these two numbers to get the total mass of the nucleus, and this tells us that lithium-7 should weigh 7.0567 U. But it doesn't. It actually weighs 7.016 U. Let's take a little break here to look at the periodic table, which tells us that lithium has an atomic weight of 6.941. But remember, that's a weighted average of all lithium isotopes, and we're only talking about lithium-7. You can't get isotopic masses off the periodic table. You have to get them from another source, like the chart of the nuclides that I've linked in the description below. Okay, so back to our mystery of the missing mass. We saw that lithium-7 weighs a little less than we expected to, and this difference in masses is what we call the mass defect. So where did that missing mass go? You probably don't remember this, but early on in this course, when I talked about the conservation of mass, I said something like mass doesn't appear or disappear, and of course, I put an asterisk on that statement, and the note at the bottom said, usually. This is our mystery. What causes mass to disappear like this? You may recognize the man who solved the mystery of the missing mass, Albert Einstein. In fact, you've probably even heard of the equation he used to describe the solution to this mystery, E equals mc squared. But what does that mean? Well, you might remember that we use c to represent the speed of light. Here, we're multiplying the speed of light by m, not just a generic mass in this case, but our mass defect. When we do this, we get a value for energy represented by an E. In other words, you can convert mass into energy and vice versa. In reality, conservation of mass and conservation of energy aren't separate principles. What we really have is conservation of some combination of mass and energy. When nucleons come together to form a nucleus, they lose mass in the process. That mass turns into a special kind of energy that we call binding energy, which serves to hold the nucleus together. We'll talk more about what this binding energy actually does soon. For now, we're going to practice calculating the binding energy of a nucleus. Let's look at the steps to do this. First of all, calculate the expected mass of the nucleus. To do that, figure out the numbers of protons and neutrons and multiply by the mass of each particle. Add these numbers to get the expected mass. Note that I put 4 decimal places here for simplicity, but we actually know these masses to about 10 significant figures. Next, calculate the mass defect by subtracting the actual mass from the expected mass. You just calculated the expected mass in part 1. I'll always give you the actual mass of an isotope in the problems we do in class, but if you want to find the values for yourself, look on the chart of the nuclides. This will give you a value for the mass defect in unified atomic mass units, but we're going to need that mass in kilograms for our calculations. So next up, we have to do that conversion. Now, take your mass defect in kilograms and plug it into the Einstein equation. This will give you a value for energy in joules. This is the end of the basic process, but sometimes you'll have to do one or more extra steps. For example, sometimes it's fine to leave the answer in joules, but sometimes you'll need to have this answer in electron volts, which is a unit that works very well for atomic scale processes. Finally, in some cases, it's important to know the binding energy per nucleon. Divide the binding energy by the mass number of your isotope to get this answer. We'll talk in class about why this is important. So let's work a couple of problems. To start, we'll finish calculating the binding energy for lithium-7 since that was the example we started with. First, we calculate the expected mass of the nucleus, and I'll run through this calculation pretty fast since we basically did it before. We have 3 protons times 1.0073 U per proton, which gives us 3.0219 U. And we have 4 neutrons times 1.0087 U per neutron, which gives us 4.0348 U. Adding those two masses, we get a total expected mass of 7.0567 U. Now we calculate the mass defect by taking our expected mass of 7.0567 U and subtracting our actual mass in the problem of 7.0160. This gives us a mass defect of 0.0407 U. Our next step is to convert U into kilograms. We'll multiply by the conversion factor of 1.6607 times 10 to the minus 27th kilograms. Now we have a mass value in kilograms, which we can plug into the Einstein equation. Again, c is the speed of light, 2.998 times 10 to the 8th meters per second. The m is our mass, 6.759 times 10 to the minus 29th that we calculated earlier. So let's plug those numbers into our calculator, and we get 6.075 times 10 to the minus 12th kilograms meters squared per second squared. Now those units may look a little weird, at least until you realize that a kilogram meter squared per second squared is the definition of a joule. That's why we converted to kilograms early on, so we would end up with energy units in joules. Now the problem also asked us to give the binding energy in electron volts, so let's convert that now. To do that, we multiply our energy in joules by the conversion factor of 1 electron volt per 1.602 times 10 to the minus 19th joules, which gives us 3.79 times 10 to the 7th electron volts, or another way you could say that is 37.9 mega electron volts. In general, most of your nuclear binding energies should be in the mega electron volt range. All right, let's do another problem. Here we're given the actual mass of oxygen-16 and are asked to calculate both the binding energy in joules and eV and the binding energy per nucleon. Oxygen-16 can also be written this way, which shows that it has 8 protons. But if you don't know that off the top of your head, you can look up the atomic number of oxygen on your periodic table. The fact that this is oxygen-16 tells us that we have 16 nucleons, and the math tells us that 8 of those must be neutrons. Now let's calculate the binding energy, starting with the expected mass of the nucleus. We have 8 protons times 1.0073 U per proton, which gives us 8.0584 U. We also have 8 neutrons times 1.0087 U per neutron, which gives us 8.0696 U. Adding those two masses, we get a total expected mass of 16.1280 U. Now we calculate the mass defect by taking our expected mass of 16.1280 U and subtracting our actual mass of 15.9949 U, which is given in the problem. This gives us a mass defect of 0.1331 U. Our next step is to convert U into kilograms. We'll multiply by the conversion factor of 1.6607 times 10 to the minus 27th kilograms, which gives us a mass of 2.21 times 10 to the negative 28th kilograms. Let's plug that mass into the Einstein equation. Here's our mass that we just calculated, and we'll multiply it by the speed of light, 2.998 times 10 to the 8th meters per second squared. And when we put those numbers into our calculator, we get 1.986 times 10 to the minus 11th kilograms meters squared per second squared, or basically joules. The problem also asked us to give the binding energy in electron volts, so let's convert that now using the conversion factor of 1 electron volt per 1.602 times 10 to the minus 19th joules. This gives us 1.24 times 10 to the 8th electron volts, or 124 mega electron volts. Finally, the problem also asks us to calculate the binding energy per nucleon. So let's take our binding energy. You could either use the value in joules or in mega electron volts, but I'm using the latter. And then you're going to divide that by the number of nucleons, which in this case is 16. That gives us a value of 7.75 mega electron volts per nucleon. So up until now, we've talked about nuclear energy on a submicroscopic scale, the scale of one atomic nucleus. But what about nuclear energy the way we think about it in our everyday lives? Let's talk about a reaction that might be used in nuclear energy, uranium-238 undergoing alpha decay to produce 234 thorium. This time around, even though we won't be counting up numbers of nucleons, we can still use a mass defect in conjunction with the Einstein equation. What we're going to do here is look up the masses of the isotopes in our equation. Uranium-238 has a mass of 238.0508. Thorium-234 has a mass of 234.0436. And our alpha particle, which is really a helium-4 nucleus, has a mass of 4.0026. If we add everything together on the product side, we get a total mass of 238.0462. As you can see, that's slightly less than the mass of the reactants, so there is a mass defect here. Subtracting the mass of the products from the mass of the reactants, we find that our mass defect is 0.0046 U. As usual, let's convert that mass to kilograms with our conversion factor. This gives us a mass of 1.017 times 10 to the minus 29th kilograms. All right, time for the Einstein equation. Let's plug in our mass as well as the speed of light. Our calculator tells us that this is 9.137 times 10 to the minus 11th joules. I'm not going to convert that to electron volts this time. You'll see why in a minute. As a reminder, this is the amount of energy produced by one nuclear decay of uranium-238. But what if we didn't have just one uranium-238 atom decay? What if instead we had a whole gram of uranium-238 decaying at once? Let's do some stoichiometry. Our first conversion factor uses the molar mass of U-238, so we know what fraction of a mole we have. Next, use Avogadro's number to help figure out how many atoms of uranium we have. Finally, multiply the energy we just calculated for a single uranium atom. We see that the decay of just 1 gram of uranium-238 will give us 2.311 times 10 to the 11th joules, 231.1 gigajoules of energy. Now, obviously, real life isn't quite that simple. If you actually did have 1 gram of uranium-238, not all of the atoms would decay at once. You probably remember that we did a bunch of nuclear decay problems when we studied kinetics, and uranium-238 has a very long half-life. But most nuclear reactors use more than 1 gram of U-238, and they use special techniques to make the decay go faster. Still, this gives you a good idea of how much energy you can get out of a fairly small amount of nuclear fission. Basically, a lot. There's a lot of energy stored in atomic nuclei, mostly in the form of binding energy. In this video, we've only scratched the surface of a very complex field, but at least now you have the tools to calculate nuclear energy. I hope this was helpful, and I look forward to seeing you again soon.